week. We also have a test next week. This is to finish the semester in a good mood. And also the research exercise final presentation, so don't miss it. So what is a tunnel in the context of computer networks? A tunnel is something that normally does not exist in theory, but in practice, and because this is software, so anybody can do anything practically. So many things are done, and tunnels in particular exist a lot for security, private networking, IPv6, IPv4 interworking. We will see a few examples of this. A tunnel is anything that happens when you violate the layering by putting something that of a lower layer or of an equal level into a packet of a given layer. For example, if you put a MAC layer packet inside an IP packet, which normally is the upside down approach, then it's called a tunnel. You can also put an IP packet inside an IP packet. All those things are called tunnels. Let's start with a very simple and very classical and frequent use of tunnels. Tunnels are used because people use private addresses. So most companies use private addresses for most of their internal networks. And if they interconnect them via a service, an internet service provider, of course they need to do something. Most computers inside companies don't need to talk to computers outside the world. We have seen when we talked of firewalls that for a computer inside a company to speak to something outside, usually you have to go through a firewall, and firewalls will prevent that for most cases. But they're supposed to work together, so you want to interconnect site A with site B, for example. Assume you use 10.2 and 10.1 literally in those companies, and you want to interconnect them via a provider. How would you do it? I propose here several solutions. Which one would you prefer? Oh, I have 0 solutions. One solution. This is not working? On me? It doesn't work. 117.0. Okay. Let me try again. Five more seconds. I close the poll. And of course, this is the title. Most of you would configure a tunnel, correct? You could also rent a leased line. That would probably be much more expensive. You could use modems. That's a bit old-fashioned, but that would be perhaps more secure. But you're right, the majority solution would be to use a tunnel. Homer does that. He uses an IP in IP tunnel. What does that mean? That means that you need to do a number of configuration steps. IP in IP tunnels means all the IP packets from A to B will be sent inside IP packets that will be transported by SIMSCOM that will see them as regular IP packets. For that, you need to configure in A and in B a virtual interface. There is a physical interface that goes to the ISP. You configure another interface inside this interface. And in the interface, you need to give what is the IP address of the endpoint. In router A, in this logical interface, you need to say anything that is delivered into this interface has to be sent to that address, 2222. So it's part of the interface configuration. And then you have the equivalent of link layer connections between A and B. It is as if they would be connected by an Ethernet cable, except they are connected by an ISP. So of course you need to do all the stuff you would do if they would be connected by an Ethernet cable. In particular, you need to configure routing, and packets from S to X, S is here, would be carried through this, what is called tunnel. If we observe a packet sent from S on the right to X on the left, if we observe at this point here, the observation point that is written here, what would be the IP destination address and the protocol type? It's not working again. Oh, it's disappointing. We will raise hands then. Who speaks for 1? Don't be ashamed. It's completely private. It will not be taped. So about 30%. Who votes for 2? Okay, nobody. Who votes for 3? Very few. And who doesn't know? That's the rest. Okay. So here's the histogram. 1, 2, 3, and I don't know. Well, the correct answer is 3. But I admit it's mean. It is because the protocol, the IP destination is correct. But if we use IP in IP tunnel, the protocol type is not UDP, but is IP. Right? So what we're doing here, if we're carrying an IP packet inside an IP packet, then if I do Wireshark of the IP packet, I will see an IP packet with destination 111 and protocol type IP. So there is a protocol type which is 04 for IPv4, which is 41 for IPv6. So that would be the difference. Now, of course, if your Wireshark is smart enough, it will notice it is an IP packet inside the IP packet. So you will have a second IP header that will be a 10.1. something destination address and a 10.2. something source address with a UDP port, with a protocol type, which will be UDP, but it's in the second IP header, in the interior IP header. So this is IP in IP. In practice today, if you use verbatim this case, you want to interconnect 2 private networks, you don't use IP in IP. You could use it, you should use it, but in practice you don't, because most routers do packet filtering, and when they see IP in IP, for some reason they don't like it. So they accept only UDP or TCP or ICMP. So, which is stupid, but that's the way it is. So in order to circumvent this, then we put IP in UDP. So the correct thing that is done today is you put your IP packet, this is the encapsulated IP packet, inside a UDP datagram that itself is carried inside IP. So you defeat the purpose of packet filtering. So the packet filtering rules, most of them are completely stupid. They just put a lot of complexity and are easily defeated. That's an example. You don't like IP in IP packets? Well, okay, put everything in UDP and you have the same. Similar things, at TPFL, for example, you cannot have a server on any port other than 80. But of course, then if you do anything that is not the web, for example, you will go via a web server. So that's very weak security measures. But in practice, that means this is what you will see. There is an additional header which is called L2TP, or which is the equivalent of PPP. This is Microsoft-ish type of thing. This is essentially because normally an IP packet is carried inside a layer 2 packet. And in some cases, you want to have, or one way to do it, which is again very typical of Microsoft, is to require that there is some header information beyond what is just needed by Ethernet. But for all practical purposes, this is redundant with Ethernet, so we could forget it, but it's present. So that's what we will see if we do, for example, today, a virtual private network using plain encapsulation. Of course, in practice, if you do virtual private networks, you want to add some function to what I showed here. What I've showed here is how you can use a public internet service to interconnect two islands as if they would be connected by a MAC layer service. So we use the public internet here as a MAC layer mechanism. But when you do this, usually you want more. What important additional function do you want? Well, you want some form of security. If you pull your Ethernet wires between building A and B, well, they are not secure. Anybody can sniff into, can break the wire, add a T connector and sniff with Wireshark the traffic, but it requires physical access to the wire. When you go via the internet, then of course you make the job of attackers much easier. So most solutions today would use some form of encryption. There are, roughly speaking, two ways to do it. If we go via the IP in UDP encapsulation, you would use one of the encryption and authentication solutions that, one of the many solutions that exist. One of them is called IPsec, that essentially provides both authentication, a signature, and encryption of the packet. So the packet, the blue packet, will be encrypted. So this includes everything of the packet up to down to layer 3. So this is the IP header and everything. So if an opponent, an attacker, sniffs traffic here, then this is all you will see. You will see that there is traffic between those A and B. You can even see how much traffic there is, but you cannot see which machine here is talking to which machine there, and you cannot sniff the data here. This is a technology that is used, for example, by EPFL VPN. That's one of the variants with those type of encapsulations. If you use UDP and IP, after all, you're using a transport layer association. So instead of doing IP in IP, if you use UDP and IP, then you could do a transport layer association, and you could use TCP, for example. So one very frequent use of this type of tunnels is to put IP packets into the payload of a TCP connection. This is OpenVPN, for example, which is, I guess, becoming more popular than this solution, is doing this. So in that case, you open a TCP connection between A and B, and you encapsulate all your IP packets inside a TCP connection. This has advantages and drawbacks. It has an advantage that from the viewpoint of SIPSCOM, you have one congestion-controlled connection. So the amount of traffic that goes here will obey the principles of congestion control. Depending on the application in A and B, that may be good or bad. If you have real-time constraints here, that may not be good. So there is an alternative for that, which is, so this is using TLS, which is something we have played with in Lab 3 as in the optional part, which is adding encryption to TCP. If you add encryption to UDP, you obtain DTLS. This is DTLS here, and this is also another solution that exists here. The difference in if you have UDP versus TCP is the packet is lost inside the provider domain. With UDP, the packet loss will be visible to both ends. Whereas with TCP, B and A will repair the loss here. This is used, for example, if you access the wireless LAN of EPFL not using your own credentials. So if you don't log into the EPFL wireless LAN, but you use the EPFL public wireless LAN, then you have to run a VPN to be able to get the service. I did that here, so I obtained this address, which is a private address of a wireless LAN. I connect to a VPN server, which is often called a VPN server, but is in fact a router, that terminates the tunnel. There is a tunnel between me here, and this machine, which is now a router, and this tunnel goes over the wireless LAN. So exactly like in the other case, except now on the left I don't have a router. The tunnel starts in my machine here, and you can, if you list your interfaces here, you see that there is there must be one of the interfaces. So this one is the physical interface of this machine, and here is a second interface, a logical interface, which is encapsulated in this. And you see that the IP address that is given to my machine is an IP address of EPFL. This is old of a few years ago. Today you would have 179, but the principle is the same. So I have two IP addresses, the IP address which is the IP address that I have on the wireless LAN, and the IP address which is given to me by the VPN server. Now assume B sends a packet to me, to A. So I'm logging to a server at EPFL, and that server responds with some data. How will this packet find its way? Do we need one of those solutions or nothing special? This doesn't work again, so we'll have to raise hands. Does anyone have one of those? I'm the only one with so I click. Okay. Who votes for one? Okay. Who votes for two? Who votes for three? And who doesn't know? Okay. So if we look at the addresses here, we see that the address that I have, that my PC has, is 83 dot something, so it's in the same subnet as the VPN router. So when a packet comes to me at R will do an ARP request for this to find the MAC address, and this ARP request will be broadcast in this subnet. So what happens next? We could imagine that the VPN router forwards the broadcast to A. That would mean we do ICMP ARP in the case of IPv6, or native ARP packet in the tunnel. We could imagine doing this, but typically we don't do it because those are broadcast things. The idea of broadcast is you keep that local to a local area network. You don't want to flood the broadcast too far, too much. So we will not do it in practice. We will not send the broadcasts through the tunnel. This is a router, as I said. So a router, in principle, doesn't forward MAC packets untouched. So it will not work, except, as we have seen, if the VPN router does proxy ARP, which is the correct solution here. So we will need to do proxy ARP. So this was for the basic use of tunnels. So today all VPNs use tunnels of one of the two forms I mentioned, or perhaps other variants. And another use is to solve the interworking of IPv6 with IPv4. And in particular, today we will study the like-to-like access. We have seen last week and the week before interworking scenarios with application layer gateways and NATs. Now, now we study another scenario, which is like-to-like. Like-to-like means I have IPv6, I want to connect to the IPv6 internet, but my provider gives me only IPv4 access. This is what we had at the beginning of the course on the EPFL wireless network, for example. That now gives IPv6, but the move to IPv6 occurred during the middle of the course. So that's what we say, the early adopter problem. We are early adopters of IPv6. Most people in Switzerland don't use IPv6, but in this course we do. So we are confronted with issues of having local access, which is IPv4 only. Later, one day, we'll have the opposite problem, which is that there will be lots of IPv6 and a few old stuff that are IPv4 only. We will discuss mainly today this solution. So the like-to-like problem is much easier to solve. So there are clean and well-defined solutions for that, unlike the interworking, which is always a bit acrobatic. The like-to-like solution is easily solved by tunnels. if I want to connect this to that. Since both ends are talking IPv6, the only problem is connectivity. And since I have connectivity by IPv4, then I can simply put all my IPv6 packets into IPv4 by using a protocol type IPv6 inside IPv4. So this is what is typically done. Now there are a few configuration problems you need to address if you do this. One of the configurations is the IPv6 address allocation. In this IPv6 island, which IPv6 addresses do I use? Because I don't have a provider that gives me IPv6 addresses. We could use private addresses, but if we want to connect to the IPv6 internet, that's not a good idea. So we would like to have a mechanism to get public IPv6 addresses when we are connected only to public IPv4 internet. So we need a mechanism to derive automatically a public IPv6 address from an IPv4 public address. That should not be difficult because IPv6 is very large, so IPv6 address space. So it should be possible to reserve a subspace in the IPv6 space to correspond to all the IPv4 addresses. We will see that's easy. We need also to configure the routers. We need routers like A and B that are able to do the interworking, and they need to be configured in terms of routing. So all of a sudden now we have routers that speak to routing in the IPv6 world and in the IPv4 world. How can we manage the two? We do not have routing protocols that will do the interconnection between the two. We have seen, for example, that BGP can handle IPv4 and IPv6, but that just means it can carry reachability information of all IPv4 prefixes and of all IPv6 prefixes, but it's not trying to say how do you go from one to the other. So we will not use routing protocols for that. We will use a simple trick that I will say using well-defined default addresses. And last, we would like that those tunnels are automatically done. Here I'm showing just two routers A and B. If I have just two, I can configure them manually, like Homer's case a few minutes ago. But if I have, of course in the world I will have much more than two. I will have lots of people. For example, it can be me at home if I've configured my local area network to work with IPv6. So we will have lots of A's and lots of B's. So we need a scalable way to manage all those tunnels. There's one solution to that, which is called 6RD. That's the most widespread solution today. I will not explain 6RD because it's exactly the same as 624, except for the addresses that are not the same. And there are other variants, Teredo and ISATAP, that are in the slides, but that we will not see today. Just a warning, 624 is, I think, a bad name for that. 624, for me, alludes to an interworking solution, but it's not. 624 is not how you interconnect 6 and 4, but is really, it should be called 626/4 or 646, or something like this. So how does it work? Well, first, it solved the address allocation problem very much in a similar way as we have seen for NAT64. We've seen that NAT64 had also the problems of how do I map the IPv4 address space to IPv6 if I am an IPv6 machine behind the NAT. And then we have seen that we use a block. We reserve a block, a prefix of 96 bits in the case of NAT64. Here in the case of 624, we do the same trick, but the prefix is much shorter. We'll see why. There is one prefix, which is 2002, because it was invented in 2002, 16 bits. So exactly those 4 hexadecimal digits means 624 addresses. So all addresses that start with that are reserved for 624 addresses. And if you have such an address, the things that come immediately after this prefix of 16 bits are an IPv4 address. Of course, when we will write it in hexadecimal digits, but we have 32 bits, it will be a hexadecimal address. For example, you see here this address, 202.80b2, etc. It means this is an IPv6 prefix of the 624 family, that corresponds to, that is derived from that IPv4 address. So if you see an address that starts with 2002, that means you know that the following 32 bits are a valid IPv4 address to which you can send packets. So the trick will be, well, if you build a tunnel, if you see an IPv6 address that is of that form, you know immediately what IPv4 destination address you should use. You just copy it from this address. So that's the main mechanism. So this, because we want to embed an IPv4 address in a prefix, of course, we need space after that to put the host part of the IPv6 address. This is why you have a much shorter prefix than what we had seen before. In addition, there is another prefix, 192.88.99/24, and in practice only the .1 is used. So this address means the IPv6 internet address seen from the IPv4 internet. That means if you send an IPv4 packet to this address, it will go to a relay router that makes the link to IPv6. So making the link between IPv4 and IPv6 is done by the combination of this from IPv4 to IPv6, and that 2002 is from IPv6 to IPv4. If you're in IPv6 world and you see an address like this, you know that you should send it towards IPv4. This is what this prefix means. So this 2002 prefix solves the address allocation problem. If I am at home and I receive an address like 1234 from IPv4, then I can construct an IPv6 prefix 2002 1234. Now this is a case where decimal or hexadecimal is the same, so this is the hexadecimal representation of this. This is a prefix that my 624 router or my 624 software in my PC will automatically allocate to my 624 interface. So in particular, if I do that in this router, which is what we do, for example, in the Internet Engineering Workshop when we give IPv6 service over the wireless network. We have only an IPv4 service, so we create our own IPv6 prefix by this mode. So now you have an entire local area network in which you have 48 bits, so you can use, for example, 16 bits for your own subnet, and you still have 64 bits for the host part. So you can build a very large network with connected here. Here I'm showing also Bart, who is directly connected to IPv4, but wants to run IPv6. Then he can do the same with his own address, machine address. Instead of doing it at the router, you can do it also in a host. That means Bart also, if he uses 624, can have a valid IPv6 address, even though he's not on IPv6 physically. And here I'm showing other addresses that are not IPv6, that are not 624. And this 192.88.99 IPv4 address is the IPv4 address that is given to relay routers. That means to routers that are at the interface between IPv6 and IPv4. And we will see how they are used in a minute. A router like B, in particular, will inject into routing IPv4 and IPv6 two different prefixes. A first prefix, this one, will be injected in IPv4. Of course, there will be more than one relay router. There can be a large number of them. Each of the relay routers will inject the same prefix, right? Or even the same address. They can use the /24 or the /32. Assume you have several routers that that inject the same prefix in IPv4 internet. What will be the consequence? Will it break the internet routing? Will BGP see loops or? No, it will not, because if you think about it, if you're a router, when you receive reachability information from a number of neighbors, you usually see the same prefixes coming from several directions. If you see it from only one direction, that means there's only one path towards that destination. But when you're in BGP, for example, usually there are multiple paths. So it's quite common that the same address is seen by a router as coming from different directions. So if you inject this address at different points, nothing special will happen. Routing in the internet will compute the best path, shortest path if it's inside a local a domain, best path including policy routing if it's in the global internet, to the nearest or the nearest router of this type, or the one we prefer if we use BGP. So that's for the IPv4 side. B, similarly, in the IPv6 internet, will inject the 2002 prefix. So B is a 624 relay router. It's not just a router that is dual stack, that has both v4 and v6. It's a router that takes the job of interconnecting the two. It's called a relay router. It will inject here the 2002, which means that the global, which plays the same role as that one, but in the IPv6. So when somebody, for example, will send traffic to some 624 address, it will reach the nearest B relay router from the IPv6 internet. So let's do the anatomy of a packet being sent from H1 to H3. So the packet is sent to that address. So you find it via DNS or another mechanism. So the destination address is a valid IPv6 address, which is therefore valid in this network. But how do we route to this? Well, inside your local area network, you probably have a default route to the IPv6 internet, which is your 624 relay router. So this packet will be sent to the relay router. There might be other routes inside IPv6. For example, in the Internet Engineering Workshop, we have that. So all routes that go to 2002.something might be routed locally inside my local area network using RIP, for example. But addresses like this one are not carried by RIP, so we will go to the default address. So when this packet reaches A is a 624 relay router, so it knows what to do with cases like this. It receives a packet to that destination. Now it is a 624 relay router that has now a packet to send on the IPv4 side. So it will need to send it to the nearest relay router that goes to the IPv6 internet. And this you find by sending a packet encapsulated to IPv4 address, this one, which is the address that means IPv6 internet seen from IPv4. So A will encapsulate the IPv6 packet in an IPv4 packet. That's called a tunnel. But now the tunnel is automatic. We don't need to configure any special destination. It will automatically send it to this address. From an IPv6 routing perspective, that means that A, which has received an IPv6 packet, has to apply IPv6 routing. It has to go to the IPv6 routing table. We could do it differently, but it's nicer if we do it by using the standard IPv6 routing principles. If we do this, which is, as I understand, what is done, this means you have to put a route, you have in the routing table, you have to do what you do with packets that go to the default route. So A has a default route that says everything that I don't know where to send, my next hop is this here. And this is, in fact, the IPv6 address that corresponds to that IPv4 address here. Now we have an IPv4 packet that will follow its way to the internet. It will go to the nearest B router, which is again a 64 packet. Now because B has received it on this address, it knows it's an encapsulated packet. It will decapsulate it. It will read the IPv6 destination address, but because B is on the IPv6 internet, it has a routing table and knows how to send it, so the packet will reach H3. Now, if I do a packet sniffing at 3, I look here, what is the IPv6 source address for the packet that we have just analyzed? I propose 3 possible solutions. Which one do you prefer? We'll do it manually. Who votes for 1? Okay, that was easy. Who votes for 2? Who votes for 3? Who votes for 4? And who doesn't know? Everybody knows. So we have a bimodal distribution. So that's embarrassing. Which one is correct? Well, so I'm looking at the IPv6 packet here. That means after I have decapsulated the IPv4. But what is the principle that we've done zillions of times now? If you packet sniff and you look at an IP packet, what IP source address do you see? It's always the source of the source host, not of an intermediate router. So the correct solution is this one. Right? It's not the IPv6 address of S12 of this machine, right? Because this machine, A, has just done its job of an IPv6 router. It has received an IPv6 packet, has analyzed the destination, has found that the next hop is this one, which is the IPv6 address of this multicast address, of this anycast of this that corresponds to the red address. So it has just taken the IPv6 address, encapsulated it without changing the source address, of course. So this is the correct solution. Another question now on the reverse path. Of course, packets there will be responses to whatever traffic is sent here. So at H3, we send the packet back to H1. How will this packet know that it has to go to B and not to some other machine here? So we will pull manually. Actually, we don't need clickers, right? So who votes for 1? Who votes for B? Who votes for 2? Sorry. Who votes for 3? And who doesn't know? Who votes for 4? And of course, this is the correct solution, almost, well, the nearest in the sense of routing in the global IPv6 internet, which is nearest or subject to policy routing, for example. Now BART is doing the same thing, but alone, is accessing directly IPv4 internet, which is, for example, what you're doing if you are at home and your local area network at home does only IPv4. So BART will do the same thing, but what is the default gateway for BART? Right? The IPv6 default gateway. Who votes for 1? Are you sure? Okay. Who votes for 2? Who votes for 3? And the rest? Okay. One is not possible because there's no DHCP server in this IPv4 world that will give you an IPv6 address. Now, Slack probably is the same. Slack assumes that there's an IPv6 router that will inform you of the default route to use. If there's only one IPv6 router on link with you, then this one you will adopt as your default route, but here there is not such a thing. So the only thing we can hope is solution 3, which of course has to be statically configured in your software. And this is, for example, what Windows typically does. So if you use a 624, it will configure this default address here. Oops, merci. Let's conclude with this one. Bart speaks to Homer. Which way will the packet go? If it works. Who votes for 1? Who votes for 2? Who votes 2? 2 again? Yeah, it's becoming more popular. Who votes for 3? And who doesn't know? Okay, so if you vote for 1, you're a bit pessimistic, but that's probably based on experience. Lots of things happen like this. Here it will go directly, because if we analyze what will happen here, I mean, this is a 624 host. So it has a 624 destination it sends to this address. So 624 hosts, what does it mean to be a 624? It means you are on the IPv4 internet here. So when you will send to a 624 address, the default route of, well, this route, the PC here can analyze the destination, which is this address here, and knows it's a destination 624 address. So if you're a 624 host and you send to a 624 address, you go first to your routing table, but this guy has no IPv6 routing table. So if it has no IPv6 routing table, then it will send to the default, which is to encapsulate the packet and send it to which IPv4 address? Well, to the IPv4 address 1234. So this is what it will do, hopefully. And so if you look at this next hop routing interface, you will see things corresponding to what I said here. You can try this at EPFL. You will see your own tunnels and addresses. You can ping this address, which is the IPv4 address of the IPv6 internet. If you do it from EPFL, you see that the next 624 relay router is in the switch domain and is probably at EPFL. I did it from home, and then I found a 624 relay router, which is somewhere in Germany at 160 milliseconds, which means that if I want to use this at home as a mechanism to address the IPv6 internet from my PC that has both IPv4 and IPv6, but receives only IPv4 from the provider, it will not be a very good solution. And why is it not a good solution? It is because my provider at home doesn't support 624, so I'm going to the nearest 624 relay router, which is provided by another provider. Now, and I will conclude on this and we will do a break. Assume you're an internet service provider. Would you like to provide 624 relaying service to other providers who don't bother doing it? It depends. If you're Google, yes, because you want to attract everything to you. If you're Swisscom, probably no, because you say we want people to pay for the service they obtain. This is why the practical, 624 is deployed here in our environment, but many providers that want to deploy a similar solution, they want to keep full control of the service they use. So they use what is called 6RD, which is exactly the same as 624, but the addresses, those two blocks of addresses, are replaced by blocks of addresses that are owned by the provider. So that instead of having a well-known address that anybody in the world who wants to connect you through this interconnection mechanism can use, I will have only a private address that only the telecom boxes of my provider domain will be able to access and will know. So this is a very popular deployer. An early deployer is Free in France, which is, thanks to this mechanism, so what Free does, the box like A is the telecom box of Free, the Free box. They have an IPv4 backbone, but they can give IPv6 to everybody using this mechanism. Voila. That's all we will see for 624 for the time being, at least. So we do a break, and after the break, we will switch topic and resume, therefore, in 10 minutes. It's called translation. We have seen translation when we have seen NAT64, when in order to transport the data from an IPv6 machine to an IPv4 machine, typically using NAT64, we've seen with the NAT solution, we translate the header. There are solutions that can do the same thing as 624, for example, but using translation. It's a bit complicated, and you have all the details in the slides. What will emerge in the future, we don't know. So 6RD is deployed. So 6RD is something that is used to provide today IPv6 access to local area networks that are IPv6 only, that are connected to an IPv4 infrastructure. That's one solution that works. NAT64 is also one solution that works, together with other combinations that are given in the slides. For all the others, we will see. 624, for example, does not work. 6RD works at home because typically it's implemented in your telecom box. If you're in Switzerland and you have a service from Sunrise or Swisscom that doesn't provide you IPv6 service, and you try to run 624 in your PC, like Bart in that example, it won't work because you're behind a NAT. So if you're behind a NAT, your IPv4 address is a 10 dot something or 192.168, so it's a private IPv4 address. Of course, you cannot build a public IPv6 address from a private IPv4 address prefix. So you need to know what is the IPv4 public address of your NAT, which is complicated and is done by Teredo. So Teredo is a variant of 624 that is tailored to the special case of when you're behind a NAT. That one works also. It is supported by Microsoft, so it works in fact better than 624. That gives you an idea of all the flavors of all the that can and will exist in the coming years. Computer networking is like biology. Lots of things are done, lots of things are tried. Anybody who can write C++ code can develop a new solution for any of those things. So there are plenty of them. And it is like biology in the sense that it is evolution that will take care of eliminating the solutions. What I've tried to do in this course is to give you the fundamental mechanisms, which in that case are encapsulation and translation. And then we will see whether the existing mechanisms that are in the slide will settle to one of them, or whether a new one will arrive. What I have seen in the past 20 years, I've been teaching IPv6 since 1995, and the transition to IPv6 since 1995, the mechanisms have changed over time. So many mechanisms have been tweaked. After 20 years, generations change, so after 20 years, people tend to forget what was done 20 years ago. So sometimes new things are just reincarnation of old stuff. We will probably see some of it. So the solutions that 624 that are very interesting but are very anecdotal. Only people like us here, when we want to try IPv6, then we use 624. The rest of the world, if you don't have IPv6 given by your provider, then you don't use it, period. So solutions like this might come back in another form when there are big pushes to IPv6. Whether there will be a big push to IPv6, we don't know. That's another story. You will know more in 20 years. I don't know if I'll be here to find out. But that is certainly a very interesting topic. That's what I say here. It's a lot of fun because many things will not work easily. So there is at least engineering, if not research, to do here for now.